This video introduces model-theoretic semantics. I'll provide an overview of the concept, followed by an example application. Model-theoretic semantics is a form of semantics in which the model serves as a formal construct representing a particular state of affairs in the world. Words or phrases and the corresponding meaning representation language can be mapped to elements of the model, and then we can check whether input facts are consistent with the existing model. There's some common terminology that you'll probably hear associated with model-theoretic semantics. First, a given meaning representation is characterized by both non-logical vocabulary and logical vocabulary. Non-logical vocabulary refers to the open-ended sets of names for objects, properties, and relations in the world we're representing, and logical vocabulary refers to the closed set of logical operators that are used to compose expressions. The domain of the model refers to the set of concepts, categories, or individuals being represented. Every element included in the non-logical vocabulary will correspond to a unique element within the domain, although the reverse is not necessarily true. A given domain contains objects, properties, and relations. Objects are just any element within the domain. Properties are sets of elements within the domain. For example, we might have a property purple, and its denotation would be the set of elements within the domain that are purple. Relations are sets of tuples of elements within the domain. So, for example, the denotation of the relation student in might have tuples like CS421 Ankit and CS421 Nimisha. We need to create mappings that connect our non-logical vocabulary to formal denotations in our model, and we do so by creating functions known more formally as interpretations. We can see how this works with an example application. Let's assume that we have some restaurant patrons and restaurants in our model. We have some facts about the likes and dislikes of different patrons, and we have some facts about the restaurants. We're specifically interested in 4 patrons designated by the non-logical symbols Natalie, Usman, Nicholas, and Mina. We'll refer to those elements using the constants A, B, C, and D. We're also specifically interested in 3 restaurants designated by the non-logical symbols Giordano's, IDOF, and Artopolis. We'll use the constants E, F, and G to refer to those elements. Finally, we'll assume that our model deals with 3 pretty similar cuisines in general, designated by the non-logical symbols Italian, Mediterranean, and Greek. We'll refer to those elements using the constants I, J, and K. Now, we're going to group our restaurants into a few properties, fast and table service. Fast denotes the subset of restaurants that are known to make food quickly, and table service denotes the subset of restaurants for which a waiter will come to your table to take your order. We're also going to represent a few relations. We'll have the relation like, which denotes tuples indicating which restaurants individual patrons like, and serve, which denotes tuples indicating which restaurants serve which cuisines. This means that we have the domain D containing A, B, C, D, E, F, G, I, J, and K, corresponding to the terms in our non-logical vocabulary, with some knowledge corresponding to the different properties and relations we've specified, so we can evaluate representations like Natalie likes IDOF or Giordano serves Greek by mapping objects to their corresponding domain elements and, in turn, the appropriate properties and relations. So basically, we're just using sets and then operations on sets to ground these expressions in our meaning representations. So this clearly works for simple things like Natalie likes Artopolis or Giordano serves Italian. But what about more complex sentences where we would need to combine multiple properties or relations? In cases like this, we need truth conditional semantics where we can also model things like conjunctions, equality, and negations. One meaning representation language that satisfies these constraints is first-order logic.